This is Sarah Wilkinson, professor at Humber College and the University of Guelph Humber. Today I'm going to explain how we can use the oxyhemoglobin dissociation curve to calculate the oxygen content in the blood in mils of oxygen per volume of blood. In a previous video, I've covered what exactly a partial pressure is, and I've covered how to use the oxyhemoglobin dissociation curve. I would encourage you to check out those first two videos before you come to this one to make sure you're going to follow along. This video, I'm going to show you how we can use a given partial pressure of oxygen to calculate the amount of oxygen in the blood using the oxyhemoglobin dissociation curve. So again, as a quick review, the oxyhemoglobin dissociation curve allows us to find out the saturation of hemoglobin for a given partial pressure of oxygen. So at a given PO2, what is the percent saturation of hemoglobin? So we're going to start off by finding out what the saturation of hemoglobin is in the systemic artery. And if you recall, the partial pressure of oxygen in an artery is about 100 millimeters of mercury. So what we're going to do is we're going to find the 100 value on the x-axis. We're going to go up, find the point on the curve, and extrapolate across so that we, at a PO2 of 100 in the systemic artery, hemoglobin is approximately 97% saturated. So that means essentially most heme groups within hemoglobin in that part of the blood are bound to oxygen. Very few heme groups do not have an oxygen associated with it. So knowing that hemoglobin is 97% saturated, we want to find out how much oxygen is in the blood. And to do this, we're going to use a formula. That is, the concentration or content, C, in the artery, and this is referring to the systemic arteries of oxygen, is going to be equal to the concentration of hemoglobin. How much hemoglobin is there? And generally, we express how much hemoglobin there is in grams of hemoglobin per 100 milliliters of blood. So if I was to take 100 milliliters of your blood, how many grams of hemoglobin is there? In an average male, we would find about 15 grams of hemoglobin per 100 mils of blood if he was living at sea level. Obviously, a disease state, you may have less. So for example, if you have anemia, or if you've been living at high altitude for a long period of time, you may have more. In general, females have slightly less hemoglobin than their male counterparts, except for in certain circumstances. For example, when they're pregnant. We're going to take that concentration of hemoglobin and multiply it by the amount of oxygen that could bind to 1 gram of hemoglobin if it was fully saturated. So if I had a gram of hemoglobin that had every single heme group bound to oxygen, and I had 1 gram of it, it would hold 1.34 mils of oxygen. So this is a constant. If every gram of hemoglobin in the blood was fully bound up to oxygen, that gram would hold 1.34 mils of oxygen. However, hemoglobin is not always fully saturated, so we're going to multiply that by the percent saturation. In this example, hemoglobin is 97% saturated. We're not going to write it as the number 97. We're going to multiply it by its fraction. So we're going to write 97% as 0.97. Just as if you got 97 out of 100 on your test, you would take 97, divide by 100, and on your calculator you would see it would be written as 0.97. If we now look for units to cancel out, in this circumstance, grams of hemoglobin get to cancel each other out. So our answer is going to be in milliliters of oxygen per 100 milliliters of blood, which is exactly what we wanted to find out. So what we'll do is we'll multiply 15 by 1.34 and multiply that by 0.97. And we get an answer in the systemic artery that there's approximately 19.5 milliliters of oxygen in every 100 milliliters of blood when hemoglobin is 97% saturated and the person has a hemoglobin concentration of 15 grams of hemoglobin per 100 mLs of blood. So at a PO2 of 100, hemoglobin saturation of 97%, the systemic arterial blood contains about 19.5 mL of oxygen per 100 mL of blood. And it's delivering that to the tissues of the body. So for example, it would be delivering approximately that amount of oxygen to the muscle. Now the question is, how much does the muscle take out? And we know that in the systemic veins during rest, leaving the skeletal muscle, the PO2 is approximately 40 millimeters of mercury. So the next question we're going to work on is, what would be the hemoglobin saturation at that PO2, and how much oxygen would be contained in the blood? So we're going to find, at a PO2 of 40, what the hemoglobin saturation is. And in this circumstance, hemoglobin is about 73% saturated. So at that hemoglobin saturation, how much oxygen would be contained within the blood? We're going to use the same formula again. So we're going to take the hemoglobin concentration, which has not changed. It takes days, weeks, months to change how much hemoglobin's in the blood. And we're going to multiply it by the amount of oxygen that could be bound to 1 gram of hemoglobin if it was fully saturated. But it's not. So we're going to multiply it by the actual saturation. So again, for our average male living at sea level, he would have an average concentration of 15 grams of hemoglobin per 100 milliliters of his blood. And we multiply it by the constant of how much oxygen 1 gram of hemoglobin could hold, okay, if it was fully saturated, but it's not. It's only about 73% saturated. So we're going to multiply it by our 73%. And remember to write this out as 0.73. If we multiply all this out, knowing that grams of hemoglobin cancel out, we get an average systemic venous content of oxygen at rest of 14.7 milliliters of oxygen per 100 mLs of blood. So if we now put that into our diagram here, the amount of oxygen being delivered is about 19.5 mLs, and the amount of oxygen leaving the muscle is about 14.7. That means that a certain amount of oxygen has left to go into the skeletal muscle, and that's about 4.8 mLs of oxygen per 100 mLs of blood. Just subtract the content in the venous blood from what we find in the arterial blood. And if you've watched any of my previous videos, I've talked about the AVO2 difference. That's what this is. This is the AVO2 difference. How much oxygen was extracted from the blood? And we know that this changes with exercise. So at rest, the AVO2 difference, how much oxygen left the blood to go into the tissue, is about 5 mLs of oxygen per 100 mLs of blood. And we know that this goes up as exercise intensity goes up. So we're going to now do exactly the same calculation, but look at how we derive the AVO2 difference during maximal exercise, which is about 15 mLs of oxygen per 100 mLs of blood. There's going to still be the same amount of oxygen being delivered in the systemic artery during exercise, unless we've gone to high altitude or we have some lung dysfunction, but we're talking about a normal, healthy male here. So what we're really curious to find out is how much oxygen is in the venous blood. And we know that during exercise, during maximal exercise, PO2 values in the systemic veins can go as low as 10 to 15 millimeters of mercury. So the first step will be find out what the hemoglobin saturation is at that partial pressure of oxygen, and then we'll use that to figure out the oxygen content in the systemic venous blood. So again, we're going to find our PO2 of 15 on the x-axis. We're going to find the point on the graph to find out hemoglobin saturation, which is about 25% during maximal exercise, so that you can see a whole bunch more oxygen has been unloaded at the tissue during exercise because PO2 has dropped. So our next task is to find out, when the hemoglobin is 25% saturated, how much oxygen can be found within the blood. Again, using our same formula where we take the concentration of hemoglobin, multiply it by our constant if hemoglobin was fully saturated, and then multiply by our actual saturation. Again, our average male has a hemoglobin concentration of about 15 grams of hemoglobin per 100 mils of blood. And we know that if that 1 gram of hemoglobin was fully saturated, it would hold 1.34 mils of oxygen, but it's not. It has far less oxygen bound to the heme groups. Only 1 in 4 heme groups at this point is bound to oxygen. So we're multiplying it by 25%, which gives us the content of oxygen in the systemic venous blood to be about 5 mils of oxygen per 100 mils of blood. So now, delivery is still the same, 19.5 mils of oxygen per 100 mils of blood, but the content of oxygen in the vein is much less, 5 mils of oxygen per 100 mils. That means there's a lot more oxygen that has gone into the skeletal muscle, 14.5 mils of oxygen per 100 mils of blood. That's our AVO2 difference during maximal exercise. And you can see that that increases as exercise intensity increases.